meter calibration. That's something you wouldn't normally do, and in this case I need to do it because I've performed some repairs on this meter. This meter is not highly accurate, so being able to calibrate it myself is not that much of a big deal. So long as you've got something that's at least a little bit better than this one. So this one is, I think it's about 0.3% accuracy, which we'll see in a moment. This one is 0.08% accurate. So I will use this to calibrate this. And indeed, when you calibrate it, you should, well, I'm going to calibrate it on a particular range. I believe I've actually calibrated this a couple of times, and the first time I calibrated, I hadn't fully repaired the meter. So the first part of the meter repair happened many years ago. And I decided to actually, it was missing all of the annunciators and things like so. Those little bits and pieces around the outsides and the decimal points were all missing. So I actually did the calibration that first time, and that's probably the one that you will see in this, because the second time that I calibrated after having fixed those, there was pretty much nothing I needed to change. I did twiddle the multi-tone precision resistor potentiometer, but I pretty much returned it back to where it was before. So basically what happens is if you calibrate it to a particular range, you don't calibrate every range, and your precision on the ranges that you haven't calibrated it on then fall back to your precision resistor networks. So in this particular case, so this is the manual for this meter, and so yeah, this one doesn't have the bar graph along the bottom. So that's this one here. So the 3650, there is one with a bar graph, which is 3650B there, which is obviously not the one that I have. So this particular meter, let's see, yeah, plus or minus 0.3% of reading, plus one digit. On your DC voltage, and most meters have their best accuracy on DC voltage. AC voltage, you can see here, is plus or minus 0.8% of the reading, plus 3 digits. Compared to 1, except on the 750 volt range, which is plus or minus 1.2% of reading, plus 3 digits. And so on and so forth. So let's get on and calibrate. Alright, now I need voltage source. I'm not going to bother with an insulated screwdriver. So what I'm trying to do is when that last digit flickers, how often it flickers either up or down. That tells me how close. So that should be right on the low end of the 7. So if it flicks to 8, then it needs to go down a bit lower. So that's actually dropping, fluctuating a bit there. Okay, so let's go to the 20-volt range. So 1195, 1198. Okay, so I got myself a 9-volt AC transformer plug pack. That's the AC plug pack. Now this package here should be the AC package. ADC something. Alright, so it's an ADC-HD-01-Y0801 Metex instruments. And a circuit diagram, which is not exactly what's on here, it's very close. But says it comes from that package and it was a 100 ohm adjustable resistor. Well, there's a 200 ohm pot in there, so we'll measure. So that's on the 20-volt AC range, and it's close. I got true RMS on, not that that makes any difference. Sorry about that. Not only did I run out of this space, but also did it out of shot. So that was the AC voltage adjusted. To adjust the frequency meter, I'm going to leave that bodge on there. Now, these two potentiometers, here should be adjusting the ranges. So there's 200 kilohertz and a 20 kilohertz range. So I've got my frequency meter coming in here. I've got a crow probe on there. Okay, so my crow's saying it's 193.69 in the 10 miles correct. Okay, so that's interesting. So the both the digital oscilloscope and the 10 mark correct, and the front panel meter is incorrect. Okay, so that's the 200 kilohertz range, so I'll just adjust that now. So just by luck I'm adjusting the wrong one, right? So that's a square wave. triangle wave. It's a sine wave. Turn the amplitude down. Oh, it goes off. Goes off before the 10 mark. Okay. Didn't check to see what voltage that was. 160, 180, roughly millivolts. That was the point where it switched on and so it's 1.3 volts peak to peak. Sine wave, triangle wave. So took it up to 1.5 volts peak to peak. That's right. Square wave, square-ish wave. Cool. Yeah, 20 kilohertz range. Let's drop down a decade. It is a bit wonky. Contact issue. What you're seeing there is the integration time. So it's gating the frequency, so as I change the frequency it's not using a constant current either. You can see that's just straight outright capacitor charging. Okay, let's measure capacitance. It's 20 microfarads, and this is a non-polar 10 microfarad, 50 volts. .75 on the unit T. I think I'll go. This is a dedicated LCR meter, so I think I'll go with that. 0.75. Drilling on that. Let's do a zero adjust. Negative, so we want to go positive. close enough. So now I'll just put some glue on these lower edges between the, so it's not on the wiper contacts. Probably a good idea to do it, see whether it affects the reading. At least it shouldn't when it's dry, but it might do when it's wet. But the point there being is if I get it in the right place on the pot, it shouldn't matter that it's wet. Okay, so now that the meter's back together, I did notice a little bit of an issue getting the lid on and the readings changing, but I think I've resolved that. So I'll just work my way through these voltages, the 200 millivolt range, and we're close enough. 185.8, 186. Okay, so let's go up to the 2 volt range. Let's bring her up. Okay, go up another range. So we're a little bit out on the 20 volt range. Still within specs. Close enough. Okay, so measuring AC voltage, sine waves. So that's it's okay. It's not the best accuracy. AC voltage still, just mains transformer. And that's my function generator at 49, 50 hertz. 50 hertz. Okay, so AC amps, I've got the 2 meters daisy chained and basically shorting the output of my function generator, and I just adjust the output voltage, and so the current. Nine volt AC plug pack. What is it, about 50 ohms? So there's a discrepancy there. Yeah, out by a similar amount again. DC amps. It's closer. Two milliamp range. It's fine. DC microamps. Okay, so measure capacitance. Not that I'm going to use the meter for capacitance. 1.675. So a 10 microfarad 50 volt bipolar, non-polar. 6.5. Close enough. 0.1 microfarad, 100 nanofarad. 96, 5.4 amps. Okay, frequency 200 kilohertz range. Fine. 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 So I thought I would investigate the Hfe circuit on here. So I've got a BC337 here, and I've just hooked up a couple of meters, measuring the current. So on the left, I got this one measuring the base current, and it's 7.9. Let's call it 8 microamps, and we're getting 980 microamps on this side. So and it's telling me that it's got a HFE, or a gain of 89. So the circuit diagram, as I found and have been modifying for this particular circuit, it's rather simple. The base is fed via a 270k ohm resistor, and it's going straight to V+, the positive terminal on the battery, the 9-volt battery. The collector is directly connected to V+, and the emitter has a resistor to basically the common on the ICL chip. So if you look at the ICL chip, it'll tell you that between V+ and common, it will regulate 2.8 volts. So we've got a 270k plus a diode drop across that, plus whatever voltages are developed on the emitter resistor. So now the circuit diagram, it's claims that emitter resistor is R35, and it says it's either 9 ohms or 100 ohms. So the common is connected, the common on the ICL chip is connected to the common on the meter here. So we should be able to measure those voltages. Okay, so I'm just going to bring in this LGP meter. It's not particularly accurate. And it's got like I think it's a 1 mega ohm input resistance, but anyway, it should be sufficient. So let's just drop the weight behind here. So if I measure the base emitter, right? So if we go to the common, so that will that'll be on one side of whatever the emitter resistance is. So if we going to the emitter, so we've got 9.3 millivolts. So that's pretty much, given that this meter is not going to be very accurate, that's pretty much the reading we got on there. So and the current we're talking is almost a milliamp. So I would say, just on the magnitude of that, if it was 100 ohms, it should be a lot more than that. So I'd say it's the 9 ohm resistor. In fact, we could probably measure it. And probably don't need it to be on either. So if we got that, if that's one side, if I measure on here, should use a better meter. Ohms. So that answers that question. I haven't got access. I'd have to get access to the battery to get access to the plus terminal, so I'm not going to worry about that. No, actually, that's wrong, because the collector's connected directly to the plus terminal. So if I were to measure between the base and the collector, I should get 270k. And I do. So that clarifies that circuit. So whatever's in the schematic is correct. I don't need to open it up or do anything else like that. So that brings up the obvious question: why did they choose those particular values? Interesting. And not only that, but it's what that obviously is telling me is that they're using 200 millivolts, the default 200 millivolt range, and just so when you're doing the HFE, it's just directly deriving the voltage across there, and it produces the value. So looking at the data sheets, it's actually, in addition to looking at data sheets, I looked at the circuit, the schematic for this meter. And this meter, whilst it has a very similar circuit for its transistor tester, which I've covered over, it's actually an order of magnitude higher in value, so the current values are lower. So looking at the data sheet for the 337, it has a DC current gain graph, which this is 1 milliamp. So at 1 milliamp, it expects that the HFE typically to be around about 70, 75. I was getting 90, so these are not too bad. Yeah, so it given it's 100 microamps, or 0.1 of a milliamp on the other meter. So if you look at that, that's a gain of, what was it, the 10, 20, 30, 38, just under 40. So, yeah, that's an interesting point. If you're going to be measuring HFE, what's the collector current that you're using? Because when the current gets really low, the gain is going to get reduced typically. So I should probably look at some power resistors to find it. Power transistors to see how low that would be. So this having a 1 milliamp collector current, it's actually an important figure to know. suppose I should prove that point. See, the on-semi data sheet is pretty close to the mark. Just as an aside, when I'm getting transistor data sheets, I've always preferred to get the National Semiconductor or on Semiconductor. They seem to put a lot more effort into their data sheets, at least the older ones. Now they have all kinds of graphs for VCE SAT and the gain and all that kind of stuff, whereas a lot of the other transistor manufacturers leave a lot of those graphs out of the data sheet. So it's good that you can correlate the data. I'm not even sure what brand that is.